a revision series for most important subject, that is thermodynamics. Now in this series what I am planning is we will revise all the formulas, because GATE exam is a numerical oriented exam. Formulas remembering, formulas practice is very very important to complete the numerical. That is why I have prepared all the formulas which are required for all thermodynamic units, nearly 14 to 15 units. After completion of the formulas for a particular unit, we are going to discuss some important problems. Okay. First let us take the very first one, that is basic concepts. Under the basic concepts, important formulas like Gibbs phase rule. Gibbs phase rule is used for deciding the number of informations required to look at the thermodynamic state of the system. The number of informations required for deciding the thermodynamic state of the system, F equal to C minus phi plus 2, where C equal to number of components, phi equal to number of phases, 2 represents number of basic intensive properties, namely one is pressure and other one is temperature. Okay, this formula we have clearly discussed in the classroom, right? Anyhow, in the examination, number of components will be given and number of phases are given. You are asked to decide how many number of informations are required. For example, if the number of components are given 2, and number of phases, number of components C equal to 2, number of phases phi equal to 2, then how many informations are required? The number of informations required, 2 minus 2 plus 2, 2 informations are required. Those 2 informations may be, right, pressure versus volume, or temperature versus volume, or temperature versus entropy, like this. Okay. Then look at the another important formula. Though thermodynamics is mainly dealing the heat and work are not coming under thermodynamic system properties. In fact, heat and work are coming under path dependent quantities. The path dependent quantities never be coming under a property of the system. In our entire thermal course, we have 3 path dependent quantities, namely thermodynamic heat, thermodynamic work and entropy generation. The rest of the thermal quantity generally coming under property. For deciding the property, for deciding whether the given quantity is a property or not, we have a rule, that is dz equal to mdx plus ndy. Dear friends, remember, z is coming under a property. This z is coming under property only when you try to differentiate m with respect to y, dou m by dou y at constant x, and try to differentiate n with respect to x, dou n by dou x at constant y. If these two quantities are equal, then only the z is coming under property of the system. That is the condition for property of the system, right? Similarly, look at the another important point, relation between the centigrade scale, Kelvin scale, Fahrenheit scale, Rankine scale. The Kelvin scale is the absolute temperature scale for centigrade scale, and the Rankine scale is the absolute temperature scale for Fahrenheit scale, right? Generally, thermometers are constructed with respect to reference point. The reference points are, one is boiling point of water, that is the upper fixed temperature, and other one is freezing point of water, that is the lower fixed point. So this is the relation between the, this relation already we have clearly discussed in the classroom. This is the relation between the centigrade scale, Fahrenheit scale, Kelvin scale and Rankine scale. You try to remember this relation, right, for converting from one scale of temperature to another scale of temperature. For example, if the temperature is given minus 40 degree Fahrenheit, then what is the equivalent temperature in degree centigrade? For that you take the relation between the degree centigrade and degree Fahrenheit. So C by 100 equal to F is given minus 40, minus 40 minus 32 divided by 180. Then C equal to minus 72 into 100 divided by 180. It is simply with this value we are getting minus 40. From that, the moral is the minus 40 degree Fahrenheit equal to minus 40 degree centigrade. That means at a thermometer reading of minus 40, both centigrade scale and Fahrenheit scales are coinciding. So you try to remember this relation for converting one scale of temperature to other scale of temperature. Similarly, look at the another important point. At the dear friends, remember at the same pressure and temperature, remember the volume occupied by ideal gas is more compared to volume occupied by real gas. The reason for that is, you know, in the ideal gas molecules there is no controlling force of molecule. There is no controlling force between the molecules. Since molecular attractive force is 0 in the ideal gas, the molecules which are present in the ideal gas more freely migrating from one location to another location. Because of that, volume occupied by ideal gas is always more than that of real gas at the same pressure and temperature. This is very, very important point. The meaning of ideal gas and real gas we have clearly discussed in the classroom. This is the important point. Similarly, look at the another important point, Boyle's law. You know, Boyle's law, Charles' law, Avogadro's law, Rignol's law, Joule's law. These are all coming under ideal gas laws. So the very first law for ideal gas is Boyle's law. Boyle's law states that at constant temperature, volume is inversely proportional to absolute pressure. That means if the pressure increases, volume decreases and vice versa. From that you can write that, from this you can write that product of pressure and volume is proportional to 1. For eliminating the proportional limit, you are putting a constant, therefore PV equal to a constant. Product of pressure and volume remains constant. That means product of pressure volume at state 1 equal to product of pressure volume at state 2. That is the Boyle's law. If you want to know the slope of the isothermal curve, the constant temperature process is also called isothermal process or hyperbolic process. If you want to know the slope of the constant temperature curve with a PV diagram, you differentiate this part, right? You differentiate that part, PV equal to constant, differentiate on both sides, differentiate, you will get dP by dV is equal to minus P by V. This is the slope of the isothermal curve with PV coordinate system. The negative sign indicates as the pressure increases, volume decreases, because volume is inversely proportional to absolute pressure, or absolute pressure is inversely proportional to volume for any ideal gas only. Remember this rule for only ideal gas, not real gas, for ideal gas. Okay. Similarly, look at the Charles law. Charles law states that at constant pressure, the volume is directly proportional to absolute temperature. That means if the temperature increases, right, along with the temperature, volume also increases. Similarly, if the temperature decreases, volume decreases. From this I can say that volume by temperature is proportional to 1, or volume by temperature is equal to a constant. Volume by temperature remains constant means volume by temperature at state 1 equal to volume by temperature at state 2. That is the Charles law. Okay. This is also called Charles first law or Charles pressure law. Okay. Similarly, look at the another relation called Charles second law or Charles volume law is also called as Galasic law. Galasic law states that at constant volume, absolute pressure is directly proportional to absolute temperature. You should not take the gauge pressure. You should not take the thermometer reading. Here the both pressure and temperature should be absolute form. Okay. Absolute temperature means the temperature which is decided with respect to absolute zero state or absolute 0 point. Similarly, the pressure which is decided with respect to absolute zero state is called absolute pressure. Anyhow, from this I can say that pressure by temperature is proportional to 1, or pressure by temperature is equal to a constant. Pressure by temperature remains constant means the ratio between the pressure and temperature at state 1 equal to ratio between the pressure and temperature at state 2, P1 by T1 equal to P2 by T2. The this is also for ideal gas only at a constant volume. Okay. Similarly, ideal gas equation, right, it is also called characteristic gas equation. PV equal to MRT, correct. PV equal to nRT is not correct. PV equal to MRT, correct. Okay. Remember, product of molecular weight and gas constant is the universal gas constant, RU. That universal gas constant RU equal to 8.314 kilojoules per kilomole Kelvin or kg mole Kelvin, RU value. Here M is the capital M is the molecular weight, whereas small m is the mass of the gas. R is the characteristic gas constant. That characteristic gas constant is the property of the gas, property of the material, but universal gas constant is remaining same for all gases. In terms of number of moles, how can you write NRUT? Because in the place of M, you write the N into molecular weight. The product of number of moles and molecular weight is giving the mass of the gas. Now, if you write N into M, then M into capital R is becoming the RU. So, PV equal to NRUT, correct, but PV equal to MRT. You should be very careful while you are selecting the right option. In terms of number of moles, it should be universal gas constant. In terms of mass of the gas, it should be characteristic gas constant. And remember, here P and T should be absolute temperature. You should not substitute the gas pressure. The pressure should be in absolute temperature. T should be in absolute temperature. And one more thing is, units are very, very important. For example, if you take the RU value or R value in joules, pressure should be in Pascal. If the RU or RU in terms of kilojoules, pressure should be in kilopascal. You should be very careful. We need to discuss all the formulas for all the 15 units, and we need to discuss at least 4 important problems for the each unit. We have nearly 15 units. 15 multiplied by 4 problems for each unit. 60 problems we need to discuss, and all the formulas we are going to revise. For that, we need to discuss a little bit fast. Similarly, look at another important formula. Remember, for any ideal gas, the gas which obeys all ideal gas law principles at all ranges of temperatures and pressures is called ideal gas. Strictly speaking, no gas available in the universe is following all the ideal gas like Boyle's law, Charles' law, Avogadro's law, Rigna's law. But comparatively, at very low pressure and at very high temperature, there are certain gases like hydrogen, helium, neon, argon, right? Neon, argon, atmospheric air. These are the few gases which are maintaining the behavior very similar to ideal gas behavior comparatively at very low pressure and high temperature. Dear friends, remember, the real gas behavior is also very close to ideal gas behavior, very similar to ideal gas behavior at very low pressure and high temperature. Similarly, steam, the superheated vapor or superheated steam behavior at very low pressure is very similar to ideal gas behavior. Anyhow, for ideal gas, enthalpy is depending on only temperature and internal energy depending on only temperature. But for real gas, enthalpy and internal energy both are not only depending on the temperature but also pressure and volume, right? Anyhow, for any ideal gas, enthalpy is depending on only temperature. Similarly, internal energy also depending on temperature. That's the reason while we are marking the molar diagram, that is HS diagram, the superheated temperature lines are almost horizontal in the low pressure region. That point already I have clearly explained to you. The reason why the constant temperature, superheated temperature lines under low pressure region in the HS diagram almost horizontal is, we are marking the enthalpy in the molar diagram. We are marking the enthalpy on the y-axis, entropy on the x-axis. This is the saturated vapor curve. This enthalpy line should be coinciding the superheated temperature line under low pressure region, because under low pressure region the superheated vapor behavior is very similar to ideal gas behavior. For any ideal gas, enthalpy is depending on only temperature and internal energy depending on only temperature, because Cp and Cv are remaining constant for any ideal gas. Cp and Cv never be changing with change in temperature and change in pressure for any ideal gas only. We are speaking about ideal gas. In the gate, there is no concept of real gas, right? Anyhow, for ideal gas, Cp remains same, Cv remains same, and the ideal gas are maintaining zero controlling force, right? That's the reason, right? We have concluded volume occupied by ideal gas is more than that of real gas at the same pressure and temperature. Similarly, at the same volume and temperature, pressure maintained by the ideal gas is more than that of the real gas. That point already we have clearly discussed. Similarly, look at another important point, Regnall's law. Regnall's law states that the ratio between the two specific heats, namely Cp and Cv, remains constant. Remember, the Cp always more than Cv, Cp always more than Cv for any gas. For the both solids and liquids, Cp equal to Cv. But for any gas, Cp always more than Cv. Since Cp is always more than Cv, right, the gamma, Cp by Cv is gamma called adiabatic index. That gamma is always more than 1. But remember, this gamma equal to 1 for any gas, whether that is ideal gas or real gas, only at a particular state, that is absolute zero state. Only at absolute zero state, Cp is exactly equal to Cv. Since Cp is exactly equal to Cv, at absolute zero state, the gamma will be equal to 1 only at absolute zero state. Other than at absolute zero state, the gamma always more than 1. Absolute zero state, we have discussed clearly. Absolute zero state means the state where the molecular momentum is absent. The state where the molecules present in the gas unable to move from one location to another location is called absolute zero state. The absolute zero state is happening at a temperature minus 273.15 degrees centigrade only, not Kelvin, not Fahrenheit. Minus 273.15 degrees centigrade. That means if you cool the gas, any gas to minus 273.15 degrees centigrade, at that particular state, no molecule present in the gas unable to move from one location to another location. Therefore, right, the molecular momentum is 0. That particular state is called absolute zero state. Only at that absolute zero state, Cp will be equal to Cv. Therefore, gamma equal to 1. But other than at absolute zero state, for any gas, Cp always more than Cv. Okay. Similarly, look at the another important point, relation between the adiabatic index and degree of freedom. This formula already we have clearly discussed. The adiabatic index gamma equal to 1 plus 2 by f, where f equal to what? F equal to degree of freedom. F equal to degree of freedom. The degree of freedom we have clearly discussed. Degree of freedom F equal to 3. Degree of freedom F equal to 3 for monatomic gas. Monatomic gas. Right? Degree of freedom F equal to 5 for diatomic gas. Diatomic gas. Degree of freedom F equal to, right, 6 for triatomic gas. Triatomic gas. If you substitute these values, right, you can get the gamma equal to 1.67 for monatomic gas. Gamma equal to 1.4 for diatomic gas. Gamma equal to 1.33 or 34 for triatomic gas. Okay, try to remember the degree of freedom and gamma value. There is a chance to ask one more question, right, on degree of freedom. Similarly, for ideal gas mixture, right, remember the mixture of two or more ideal gases can be homogeneously mixing. Homogeneously mixing means throughout the system, pressure and temperature remains, pressure remains same at all locations. Similarly, temperature is also means temperature is uniform because of the uniform mixing, like how the milk and water can be homogeneously mixing, but kerosene cannot be mixing uniformly with the water. That's why mixing of kerosene with water is the heterogeneous mixture, whereas mixture of water and milk is coming under homogeneous mixture. Similarly, mixture of petrol vapor and air particles for the petrol engine is also called spark ignition engine, is also homogeneous mixture. Whereas in the diesel engine, mixture of diesel vapor and air particles for the diesel engine is the heterogeneous mixture, because the uniform mixing of the diesel vapor with the air cannot be possible for the diesel engine. The main reason for that is, in case of diesel engine, the diesel particles are made to enter to the engine cylinder at the end of the compression process. There is no sufficient time. But in case of what petrol engine, in case of petrol engine, the petrol particles are entering during the suction stroke itself along with the air particles. Therefore, proper mixing of the air and petrol particles are possible for the petrol engine. That kind of mixture is coming under what homogeneous mixture. Similarly, ideal gas mixtures can be homogeneously mixing. The total mass of the ideal gas mixture equal to sum of the individual masses, m1 plus m2 plus m3 plus so on. m1 is the mass of the one ideal gas in the mixture. Similarly, m2 be the mass of the another ideal gas in the mixture. Similarly, total number of moles in the mixture. Total number of moles in the mixture equal to sum of the number of moles of the each and sum of the number of moles of the different ideal gases present in the mixture, n1 plus m2 plus n3 plus so on. Similarly, look at the definition for mass fraction. Mass fraction x equal to mass of an ideal gas in the mixture by dividing by total mass of the ideal gas mixture. Similarly, mole fraction, number of moles of one ideal gas in the mixture dividing by total number of moles is giving the mole fraction. Okay, dear friends, remember here the mass is coming under extensive property, total number of moles also coming under extensive property, right? And another important point is sum of the mass fractions equal to 0, that is m, right? Mass fraction we have denoted with x, na? Okay. Sum of the mass fractions equal to 1 and sum of the mole fractions also equal to 1. Here mass fraction we have denoted in the earlier slide. What is the mass fraction? Mass fraction equal to what? Mass fraction denoted with the x, na? Therefore, I can say that x1 plus x2 plus x3 plus so on is equal to 1. Similarly, sum of the mole fractions equal to 1 means y1 plus y2 plus y3 plus so on is equal to 1. Try to remember, right? Similarly, look at another important point, pressure fraction. Partial pressure of one gas in the mixture dividing by total pressure is the pressure fraction. What is meant by partial pressure? Partial pressure is like this. The definition for partial pressure is like this. You take different ideal gases in the container. So this is the container is maintaining the ideal gas mixture. Assume that ideal gas mixture is available at a temperature 300 degrees centigrade and volume of the container where the ideal gas mixture available is some 3 meter cube. Assume this ideal gas mixture is having 4 components like 1, 2, 3, 4 like this, 3, 4 like this. Now what you do is, to decide the partial pressure of one ideal gas in the ideal gas mixture, you separate one ideal gas, let us say nitrogen, oxygen like that. You try to separate one ideal gas from the mixture and you place that separated ideal gas in the other container where the temperature equal to mixture temperature and volume equal to mixture volume. Then whatever the pressure, this separated nitrogen gas or separated individual gas alone is maintaining corresponding to mixture temperature and mixture volume is called the partial pressure. That partial pressure of that particular gas divided by total pressure is giving the pressure fraction. Here remember, the total pressure according to Dalton's partial pressure law, partial pressure of the one gas plus partial pressure of the second gas plus partial pressure of the third gas like this. Similarly, volume fraction, reduced volume, the ratio between the reduced volume and the total volume is giving the volume fraction. Reduced volume means, right, the same way you can decide the reduced volume. You take the ideal gas mixture, assume that ideal gas mixture is having 4 ideal gases like 1, 2, 3, 4. That ideal gas mixture is available with a pressure 20 bar and temperature equal to 300 degrees centigrade. Then you try to one ideal gas, you try to separate one ideal gas from the mixer. You place that ideal gas, separated ideal gas from the mixer with the mixer pressure. That means separated ideal gas is placed with mixer pressure 20 bar and to maintain the mixer temperature 300 degrees centigrade. With this combination, whatever the volume that separated one ideal gas is maintaining is called reduced volume. That reduced volume by total volume of the mixture is giving the volume fraction. Understood clearly? Yes. Similarly, look at the another important point. Dear friends, remember mole fraction, pressure fraction and volume fraction always equal. That means the mole fraction equal to pressure fraction is equal to volume fraction. Okay. Similarly, look at the another important point. Cp of the mixture. For the mixture, Cp equal to, right, mass fraction multiplied by mass fraction of the one gas in the mixture multiplied by Cp of the gas, Cp of that particular gas in the mixture plus x2 Cp2 plus x3 Cp3. That means x1, x2, x3 are the mass fractions of that particular components. Cp1, Cp2, Cp3 are the specific heats of that particular components. Cp can be decided like this. You know, there is a Mayer's equation, Cp minus Cv is equal to R. Cp minus Cv equal to R. And you know, Cp by Cv equal to gamma. From this I can write that Cp equal to gamma Cv. Cp minus, right, of course in place of Cp I can write gamma Cv. 1 minute, should be very careful. In the place of Cp, let me write gamma Cv minus Cv equal to R. From this, write the Cv outside, gamma minus 1 equal to R, or Cv equal to R by gamma minus 1, that is the Cv. Then what is the Cp? Cp equal to gamma Cv, gamma into Cv equal to R by gamma minus 1, okay. Now dear friends, remember the product of molecular weight and specific heat is called molar specific heat, denoted with C bar. Once again, the product of molecular weight and specific heat is called molar specific heat. Similarly, the product of molecular weight and Cv is giving the molar specific heat at constant volume. Similarly, m into molecular, this is the molecular weight, not mass of the gas. Molecular weight multiplied by Cp is giving the Cp bar. Now here I can also write Cp bar like this. Cp bar equal to what? Right, m into Cp. Cp equal to what? Gamma R by gamma minus 1. Let me write gamma by gamma minus 1 outside. What is the product of molecular weight and gas constant? Universal gas constant. That means the molar specific heat at constant pressure equal to gamma Ru by gamma minus 1, whereas just specific heat equal to gamma R by gamma minus 1. Here gamma is the adiabatic index, that is depending on the type of gas. R is the characteristic gas constant, that is the property of the material or property of the gas, whereas Ru is the universal gas constant. Similarly, look at the Cv for the mixture, x1 Cv1 plus x2 Cv2 plus x3 Cv, like that. Similarly, gamma for the mixture. If you want to find the gamma for the mixture, you try to decide the Cp of the mixture and Cv of the mixture. The ratio between the Cp of the mixture and Cv of the mixture is giving the gamma for the mixture. Okay. Similarly, look at the another important point. The molecular weight of the mixture. Mixture molecular weight equal to mole fraction of one gas multiplied by molecular weight of that gas plus mole fraction of the second gas multiplied by molecular weight of the second gas in the mixture plus mole fraction of the third gas in the mixture multiplied by molecular weight of the third gas in the mixture. So this is how you can decide what molecular weight of the mixture. After you are deciding the molecular weight of the mixture, the gas constant for ideal gas mixture can be decided Ru by molecular weight of the mixture. Ru, universal gas constant, is 8.314 kilojoules per kilomole Kelvin or kg mole Kelvin. That Ru by mixture molecular weight is giving the gas constant for that particular mixture. I hope all of you clearly understood. Similarly, so Okay, with that, no, the important formulas for the basic concepts of thermodynamics completed. Important questions prepared for you. Look at the very first question. Try to answer. Which of the following set of quantities contains intensive variables, means intensive properties? Pressure, temperature, density, work, energy, weight, mass, volume and area, kinetic energy, potential energy, and IE means internal energy. Which is the correct option? Yes, absolutely correct. Pressure is intensive property, temperature is intensive property, similarly density. All these are intensive properties. Option A is absolutely correct. This kind of question is generally asking for 1 mark. Similarly, look at the another important question prepared for you. The expression du equal to C. These are all the questions which were asked in different competitive exams. Okay. So, the expression du equal to Cv dt is valid for, look at the different options. An ideal gas regardless of the process. B, a real gas, a real substance at constant pressure. Option C, a real substance independent of volume and pressure. All real gases at high pressures. Right, that du equal to Cv dt. Similarly, dH equal to Cp dt only for ideal gas. Absolutely correct. You are all correct. No one is given wrong answer. Everyone is correct. Similarly, look at another important question asked for, right, one of the competitive exams. For which of the following situations zeroth law of thermodynamics will not be valid? For which of the following situations zeroth law of thermodynamics will not be valid? Option A, 50 cc of water at 25 degrees centigrade are mixed with 150 cc of water at the same temperature. B, 500 cc of milk at 15 degrees centigrade are mixed with 100 cc of water at the same temperature. 5 kg of wet steam at 100 degrees centigrade is mixed with 50 kg of dry and saturated steam at 100 same temperature. 10 cc of water at 20 degrees centigrade are mixed with 10 cc of sulfuric acid at 20 degrees centigrade. So, you are asked to decide for which of the following situations zeroth law of thermodynamics will not be valid. Which is the correct option? Can you answer? What is the zeroth law of thermodynamics? Zeroth law of thermodynamics states that if two bodies are separately thermally equilibrium state with the third body, then any two bodies are under thermally equilibrium state. Look at the option D. 10 cubic centimeters of water at 20 degrees centigrade are mixed with 10 cc of water with sulfuric acid. There is a chemical reaction between the sulfuric acid, right? Because of that chemical reaction, right? Chemical reaction concept is not, right? Chemical reaction concept is not involving with the zeroth law of thermodynamics. Anyhow, if you mix the water with the sulfuric acid, there is a chemical reaction. Chemical reaction concept is not involving with the zeroth law of thermodynamics. That's why option D is a incorrect statement with respect to zeroth law of thermodynamics. Therefore, option D is absolutely correct. Okay, there is no temperature change by the time 50 cc of water mixing with 150 cc of water at the same temperature. Temperature remains same. Similarly, by the time we are mixing the 500 cc of milk at 15 degrees centigrade with 100 cc of water at the same temperature, there is no temperature change. But in the last case, because of the chemical reaction, temperature may be changing. Though initially both are maintaining, water and sulfuric acid are maintaining same temperature. Okay. Anyhow, D is the incorrect statement, invalid statement for zeroth law of thermodynamics. That invalid statement is our option. Option D is absolutely correct. Okay. Similarly, look at the another important question asked in the one of the competitive exams. These are all the different questions asked in different competitive exams. A scientific law is a statement that A, we postulate to be true, B, is generally observed to be true, option C, is derived from the mathematical theorem, option D, is a summary of experimental observations. There is no mathematical relations for any thermodynamic laws. All thermodynamic laws are completely based on experimental observations. I explained to you clearly by the time we were discussing the laws of thermodynamics. There are 4 laws for thermodynamics: zeroth law of thermodynamics, first law of thermodynamics, second law of thermodynamics, and third law of thermodynamics. All the 4 laws of thermodynamics, right, are completely based on experimental observations only. There is no mathematical proof for the all laws of thermodynamics. And another beauty of laws of thermodynamics is there is no controversy between the 4 laws of thermodynamics, and there is no controversy between these laws of thermodynamics with other laws available for other branches of engineering. Anyhow, the scientific laws are decided, scientific laws are framed based on the experimental observations. Option D is absolutely correct. So, these are the 4 problems or 4 questions I prepared for basic concepts of thermodynamics. Okay, having that, let us take the second unit formulas. That is work and heat, right? Second unit formulas, work and heat. Now let us take the important formulas for work and heat. Okay, remember heat transfer. The heat transfer and work transfer are not coming under thermodynamic system properties. In fact, both heat transfer and work transfer are coming under the path dependent quantities or path function quantities. Okay, area below the TS diagram is the heat transfer, and area below the PV diagram is the work transfer, because the thermodynamic work for a closed system equal to PdV. Okay, and another important information is both heat and work are not coming under storable form of energies. General formula for finding the heat transfer is Q equal to mc into dt. Okay, if your process is at constant pressure, then the heat transfer at constant pressure equal to, in place of C, you write the Cp, mcp into dt. Similarly, heat transfer at constant volume equal to mcv into dt. Okay. Similarly, the displacement work, it is also called non-flow work. Non-flow work is equal to integral 1 to 2 PdV or simply PdV. Since the PdV is the displacement work or non-flow work, area below the PV diagram. Let us say if I mark the PV diagram like this, pressure versus volume like this, right? The process may be represented like this. The process may be represented like this. It is a straight line, let it be. Then area below 1 to 2, up to volume coordinate. Area below 1 to 2 up to volume coordinate is the displacement work. This is the displacement work. So, this is the displacement work. The displacement work equal to integral 1 to 2 PdV. That means area of that particular 1 to 2 is giving the displacement work. Similarly, look at the another important point. For any thermodynamic cycle, according to first law of thermodynamics, cyclic integral del Q equal to cyclic integral del W. Its meaning is net heat transfer is equal to net work transfer. Remember, this is valid for only thermodynamic cyclic process like Otto cycle. If I take the Otto cycle, as you know, Otto cycle consists of mainly 4 processes. The Otto cycle is like this: pressure versus volume diagram, right? Pressure versus volume. The Otto cycle, this is the isentropic compression, reverse adiabatic compression, followed by 2 to 3 constant volume heat addition. Similarly, reverse adiabatic expansion, and 4 to 1 isochoric or constant volume heat rejection process. Let us mark the heat interactions and work interactions. For 1 to 2 heat interaction is Q1, work interaction is W1. For 2 to 3 heat interaction is Q2, work interaction is W2. For 3 to 4 heat interaction Q3, work interaction W3. And for 4 to 1 heat interaction is Q4, work interaction is W4. Then the meaning of net heat equal to net work means sum of the heat transfers equal to sum of the work transfers. It means Q1 plus Q2 plus Q2 plus Q3 plus Q4 must be equal to W1 plus W2 plus W3 plus W4. That is the meaning of net heat transfer equal to net work transfer for any thermodynamic cycle. Similarly, look at another important point. For any thermodynamic system, the cyclic integral del Q cannot be written as Q2 minus Q1, because the work and heat, because heat and work both are not only depending on the initial state and final state, but also the route followed by the process. That's why path function quantities never be written by their difference. Similarly, integral 1 to 2 del W should not be written as W2 minus W1. But how can you write? So it can be written as integral 1 to 2 del Q can be written as either Q1 to 2 like this, or Q1 to 2 like this, or simply Q. Similarly, integral 1 to 2 del W cannot be written as W2 minus W1, because work is not only depending on the initial and final state, but also route followed by the process. Therefore, it should not be written by their difference, but it can be written as W1 to 2 like this, or W1 to 2 like this, or simply W. Because the work is not only depending on the initial and final state, but also depending on the history of the process or path followed by the process, right? So, but properties like pressure, pressure, temperature, volume, these are all coming under properties. Properties are depending on only the initial state and final state. The properties do not care what is happening between the state 1 and state 2. Once we reach to state 2 from state 1, either by reversible manner or irreversible manner or different paths, right? Once the initial state and final states are identical, the property remains same, because property does not depend on the route followed by the process or history of the process. Like how we are having our own properties. My family is having own properties. I have land, I have gold, I have civil. Even I am teaching at this moment. Even I am teaching for you or some other students. My property value at this time cannot be changed. Let us say I have some X bank balance. That X bank balance cannot be changed. Even I am teaching either in Hyderabad or Delhi or Pune at this moment. But love and affection, whatever we are maintaining with our family members or relatives or our friends, that love and affection is going to change from one location to another location. Therefore, love and affection is coming under path dependent quantity for our life. Whereas, whatever the bank balance, whatever the gold, whatever the silver, whatever the land, whatever the apartments we are maintaining, that is our family property. That family property cannot be depending on the path following, but the love and affection is depending on the path following. That's why love and affection is a path function quantity, like heat and work are coming under path function quantities for thermodynamic systems. But pressure, temperature, these are all the properties. Properties can be written by their difference. Integral 1 to 2 dP equal to P2 minus P1. Similarly, integral 1 to 2 dt equal to T2 minus T1. Similarly, integral 1 to 2 dH equal to enthalpy of property can be written as H2 minus H1. So, all properties can be written by their difference, but path function quantities never be written by their difference. Similarly, look at the another important point. Point function quantities can be written by their difference. Right. Okay. Anyhow, point function quantities can be written by their difference. That point already we have discussed. Whereas path function quantities cannot be written by their difference. Very, very important point. Similarly, look at the another important point. Cyclic integral path function quantity never be equal to 0, whereas cyclic integral point function quantity equal to 0. That means the net change in property for any thermodynamic cycle always equal to 0, but net heat transfer or net work transfer never be equal to 0 for any thermodynamic cycle. This is very, very important point. Remember, this symbol is used for only for thermodynamic cycle. Cyclic integral is for only thermodynamic cycle. It represents cyclic integral means sum for a complete cycle. SUM sum, it is equal to SUM sum for a complete cycle. Okay. Similarly, cyclic interval point function quantity always equal to 0. Okay. So with this, the formulas and important points for the work and heat completed. Important questions from the work and heat. Look at the first question. First question means first question in the work and heat. If a quasi equilibrium process exists, we have assumed the pressure at any state may be missing, constant to be everywhere constant. Okay, that point is not, but it is one of the competitive exam question asked like this only. An isothermal process that no friction exists, the boundary motion to be infinitesimally small. If a quasi equilibrium process exists, we have, which is the correct option? Can you answer? So answer is option D is absolutely correct. Option D, no, not option G. The pressure at any state, no, in the quasi static process, all the properties are uniform in the entire system. Since pressure is also coming under one of the property, the pressure at any state is uniform throughout the system. Therefore, option E is absolutely correct. Now come to the option D, the boundary motion to be infinitesimally small. That is also looking correct. But quasi equilibrium, quasi plus equilibrium. Even if the boundary is moving with infinitesimally small or boundary is moving with at very slow speed, if the friction is existing, for the last option, the properties need not be maintaining the uniform throughout the system. And look at the C, that no friction exists. No, though the friction is not existing, if the process is happening fastly, like how the gas is compressing fastly with the centrifugal compressor and axial flow compressor, that process need not be coming under a quasi equilibrium process. So quasi static process is the very, very slow process where friction is absent, and the properties in the system are uniform throughout the gas present in the system. Therefore, option A is selected. It is the option A is missing some clarity, but it is asked as it is in one of the competitive exams. So option A is correct. Option C is not correct, because though it is given no friction exists, if the process is happening fastly without friction, that need not be taken as quasi equilibrium. Option D also not correct. It is given the boundary motion to be infinitesimally small. If the friction is existing, even if the boundary is moving very slowly, that never maintaining the quasi equilibrium. I hope all of you clearly understood. For this particular question, option A is absolutely correct. Let us take the next question. Look at the next question. All of you try to read the next question available for you on the screen. It is asking an insulated rigid vessel containing some gas and a electric resistor. In a certain interval of time, the resistor connected to an external electric power source heats the gas. Considering the vessel and its contents as system, different options are available. Option A, heat and work transfers are 0. Option B, heat and work transfers are positive. Option D, heat transfer is 0 but work transfer is negative. Option D, heat transfer is positive and work transfer is 0. Try to get the answer. Option C is absolutely correct. For this question, option C correct, because it is given. Look at the board, all of you. It is given an insulated rigid vessel. This is your vessel. This is insulated. It is perfectly insulated. Once it is perfectly insulated, no chance to have the heat transfer. Therefore, heat transfer Q equal to 0. Q equal to 0. And it is given a rigid vessel. Rigid vessel means the boundary cannot be moving. Therefore, expansion work equal to 0. Expansion work or boundary work is 0. But what is given? Electric heater is connected. Na? Let us connect the electrical heater. This is your electrical heater. And some gas is there inside the system. In a certain interval of time, the resistor connected to external electric power source heats the gas. That means electrical energy is supplied to the heater. Then what is happening? Temperature of the heater. Electrical energy is converted to thermal energy. That thermal energy is causing for increasing the temperature of the heater. Then the heat transfer is happening, right? The heat transfer is happening from heater to gas. The gas will be heating, but here that container is our system. Container is our system. Since container is our system, right? With respect to whole container, here electrical energy crossing the boundary of the system, that electrical energy is coming under work energy. Here work is entering into the system. Work enters to the system is taken as negative. That means your expansion work is 0 or boundary work is 0, but work is or energy is transferring due to electrical voltage potential difference between the system and surroundings. The kind of, there are only two energies are crossing the boundary of the system in the absence of the mass interaction. One is heat energy, other one is work energy. The energy which is crossing the boundary of the system only by temperature difference between the system and surroundings is coming under thermodynamic heat. Whatever the other forms of energies which are crossing the boundary of the system other than temperature gradient should be concluding as a work energy. Here work energy is entering into the system due to electrical energy or electrical voltage potential difference, that is taken as negative work. Therefore, heat transfer Q 0, expansion work is 0, but electrical energy is entering into system, that is taken as work energy is entering into system. Work energy entering into the system is coming under negative, work done on the system negative. Therefore, heat transfer is 0 and work transfer is negative. Option C is absolutely correct.